Respected faculty and fellow classmates, this is Animesh Das, a second year ECD student taking Science 1 this year, and this is my Science 1 project to video report on oxygen transport through myoglobin. In this project, we'll be using the idea of a spherical Galton board to look at the phenomenon. Now, moving on, let's let's look at what the Galton board looks like. Oh my god. This is what the Galton board looks like. This is a simulation over here, and before you move on, take your time, pause this video, and look at how myoglobin is different from hemoglobin, even though both have almost the same function: transport of O2 by diffusion. This is about what myoglobin does to your muscle, and this is how your myoglobin looks like. That little glob over there, that red and white, that all in red and white, that's your oxygen molecule. Using the spherical Galton board model, we are going to look at the transport of oxygen via myoglobin. The spherical Galton board will be none other than our myoglobin molecule, that globule you see, and the small glob in between that you saw over there. That's gonna be your little ball. So before we move on to what the spherical Galton board will be, to what the spherical Galton board looks like, we need to look at a 2D version of our Galton board. So here's a 2D version of our Galton board, which has a depth of n and a ball rolling all the way down to any one of these boxes. Now, our assumptions are that the ball is dropped from the topmost nail and can go either left or right only. Then let the probability of this ball going left be A and that of its going right be B. Then for an unbiased Galton board, PD of left, that is A, will be equal to PD of right, that is B. That's gonna be half. Let the total number of steps be n, and let n1 be the number of steps to the left, n2 be the number of steps to the right, and then for the ball hitting the center, n1 equals n2 equals n by 2, and also for every case n1 plus n2 is going to be n. With this being the case, let's move on to look at the probability distribution of n1. The probability that the ball takes n1 lefts and n2 rights in n steps is P, where P is n factorial by n1 factorial dot n2 factorial times A raised to n1 times B raised to n2. Now let's look at the mean displacement. Mean displacement will be n1 minus n2, the whole average, which is n1 average minus n2 average, where n1 is the mean displacement to the left and n2 is the mean displacement to the right. Let's find the average of n1, which is calculated in this way. Now observe that this could n1 times a raised to n1 could be written as a times del a raised to n1 by del a. Using this observation, we can say that average of n1 is n1 running from 0 to n factorial by n1 factorial dot n2 factorial dot b raised to n2 dot a times del a raised to n1 by del a. Interchanging the order of this differentiation and summation because differentiation is a linear operation, we get n1 average is a times del by del a of n1 running from 0 to n summation n factorial by n1 factorial dot n2 factorial times a raised to n1 dot b raised to n2. Now this little summation over here, you see this big summation over here. Well, this is a binomial expansion. This is a binomial expression. So what do you see? A times del by del a times of a plus b raised to n. That's the short of this binomial expansion. Now applying the differential over here gives me a times n times a plus b raised to n minus 1. Similarly, n2 can be written as b times n times a plus b raised to n minus 1. From equations 1 and 2, we see that the net mean is average of n1 minus average of n2, which is n times a plus b raised to n minus 1 times a minus b, which is n times a minus b. Now remember it here. Remember when I said that your board is going to be unbiased? Well, it is unbiased, and therefore what you're gonna do is take a equals b, as has been stated before, which leads us to the net mean being 0. Now look at the mean square displacement. Let the net displacement be n. Well, remember this and remember this here. So m equals n1 minus n2. Let the net mean square displacement. Note, this time it's the mean square displacement. It's gonna be m square the whole average, which is n1 minus n2 the whole square average, which is n1 square average plus n2 square average minus 2 times n1 n2 the whole average. Because for an unbiased model, n1 equals n2, so n1 times n2 the whole average is gonna be 0. Therefore m square equals n1 square plus n1 square average plus n2 square average. That's gonna be our m square average. M square average, remember m square average, what m square average is. Now n1 squared is this. Using this observation over here, we could say n1 square is this times this. This differential operator cascaded could be interchanged with the summation, which gives us this. Which gives us this summation inside this differential cascade operator. Now this is a binomial expression again, which gives us a times del by del a of a times del by del a of a plus b raised to n, which is ending up to be this. Now simplify this using a plus b equals 1 and 1 minus a equals b. That gives you this. Similarly, n2 squared the whole average could be written as this, and m squared the whole average is gonna be n1 squared plus n2 squared, which ends up being this. Now that we understood the analysis of a 2D Galton board, we are going to model the myoglobin as a spherical Galton board. But wait, why this? Rather, how so? Well, myoglobin can be considered as concentric spheres consisting of arrays of equally distributed nails. These nails make up your Galton board, and since this is in 3 dimensions, so this is a 3D Galton board. Also, the ball on the Galton's board can be assumed to be an oxygen molecule, O2, because the size of the O2 molecule is much lesser than the size of the myoglobin. So to investigate the transport of O2 in myoglobin, a spherical Galton board is suitable. Now, let the axis from the center to the sphere surface be the z-axis, and let this radius on the sphere be of n steps. In each step, the ball can go in 4 directions. Let's say left and right on the x-axis and back and front on the y-axis. Let probability for the ball moving left is p, to the moving right is q, moving front is r, and moving back is s. For equally placed nails or lanes or obstacles and unbiased board, p, q, r-ness are going to be equal to 1 by 4. If total number of steps is n, then let n1, n2, n3 and n4 be the number of steps to the left, right, front and the back respectively. then we see that n1 plus n2 plus n3 plus n4 is gonna be n, which is pretty obvious. Now, for the ball to hit the center, n1 and n2 have to be equal. Similarly, n3 and n4 have to be equal. Now, the probability distribution is to be looked at. The probability that the ball takes n1, n2, n3, and n4 steps to the left, right, front, and the back respectively is n factorial by n1 factorial times n2 factorial times n3 factorial but times n4 factorial. This whole thing multiplied by p raised to n1, q raised to n2, r raised to n3, and s times s raised to n4. Also, look at the mean displacement now, with this being your reference. Now, there will be a displacement on the x and the y axis, both displacements being independent of each other. Let the net displacement be d. Displacement on x-axis in that case will be L, and that on y-axis will be n. Then d can be written as a complex number L plus jm. This complex number taken average will be L averaged plus j times m averaged. Taking the magnitude gives us L average the whole square plus m average the whole square. Finding L and finding m requires us to find n1 average, n2 average, n3 average, and n4 average. n1 average can be found in this way. Using this observation, we can say that n1 equals n factorial by whatever this is times q raised to n times r raised to n3 times s raised to n4 times p times del p raised to n1 by del p. You can now, as usual, you know the drill, right? P times del by del p, and this summation operator can be interchanged, which gives us a multinomial expansion, which gives us p plus q plus r plus s raised to n, on which this operator is being applied, p times del by del p. This gives us p times n times p plus q plus r plus s times raised to n minus 1. Since this is 1 again, so it's p cross n cross 1. Again, p equals q equals r equals s, which gives p equals 1 by 4, so n by 4 is what we need. That's n1. A similar calculation applied on each of these averages gives us n1 as pn, n2 as qn, n3 as rn, n4 as sn taken when and each of these is taken as average, and each of these averages end up to be n by 4. Therefore, L average and M average end up being 0, which means D average ends up to be 0. So the mean displacement is 0. Now, we are going to consider the mean square displacement. Assuming net displacement as before, and L equals n1 minus n2, m equals n3 minus n4, we see that D is under root of L square plus m square. This time it's by the Pythagoras theorem of hypotenuse. Now, D square is L square plus m square, the whole under root, the whole square. That is L square plus m square. So D square is L square plus m square. So now we're going to take average on both sides, which means D square is L square plus m square, which is n1 square plus n2 square plus n3 square plus n4 square minus 2 times under root n1, n2 the whole average minus 2 times n3, n4 the whole average, and these are going to end up as being 0 because both are independent, right? So D square is n1 square plus n2 square plus n3 square plus n4 square, and L square is mean square displacement on x-axis, m square that on y-axis. Already mentioned. So n1 square can be calculated as this, and using n square x raised to n as this, where x is this and x is either of p, q, r, s, n is either of n, I running from 1 to 4. n1 square could be written as this. after interchanging the order of sum and differential, this could be this is what you get. Okay, now this is a multinomial expression, so what we get is this. Take your time, note it down. This is what the differential over here, the differential over here ends up becoming. And since p plus q plus r plus s is equal to 1, so n1 square ends up being this. And you can find n2 square, n3 square and n4 square in a similar manner, which gives you d square equals n1 square plus n2 square plus n3 square plus n4 square. Plug in all those values you got and plug in the conditions for unbiased board, and voila, there's your answer. N times n plus 3 divided by 4. So you see, this is how you could mathematically model oxygen transport through myoglobin. Never thought this could affect a game so trivial could be used to model such a fundamental process of living beings. Thank you very much.